Here's an elegant linear algebra puzzle that's a genesis of the subject of symplectic geometry. And as a bonus at the end of the video, I'll explain the connection to symplectic geometry. But our puzzle is, can you find a 2025 by 2025 matrix? This is the year 2025 when I'm recording it. Whatever year it is for you, you can ask the same question. Invertible skew-symmetric matrix. Can you find such an invertible skew-symmetric matrix? And we're going to walk through the thinking process, a beautiful little puzzle and trick. So what we're going to do is, we're first going to quickly review what this means and understand the problem. Okay, so skew-symmetric matrix basically means that A transpose is equal to negative A. Okay, so what is the transpose of a matrix? If you have a 2 by 2 matrix, and we're going to review skew-symmetry here and really get some nice examples under our belt as well, we can sort of think of this as our matrix. Our transpose is simply you reflect in the diagonal. Okay, so you reflect all the entries in the diagonal, which is this diagonal I've dashed here. So the entries in the diagonal are unchanged. Otherwise, if this is A, then our A transpose becomes, we just flip it, so A12 becomes A21, and A21 becomes A12. And otherwise, our entries are the same. Okay, so that's a 2 by 2 case. So that's our symmetry, that's our transpose. And now to say that A transpose is negative A, what does that mean? Well, if A transpose is negative A, that means each entry on the diagonal is negative of itself. But that's impossible unless each entry on the diagonal is 0. Okay, so first of all, for a skew-symmetric matrix, this is generally true because you're reflecting in the diagonal and you're saying that should be negative of the matrix. All the entries on the diagonal are going to be 0. And then you also know, because you're flipping and saying that you want A transpose, you flip these two and you want them to be negative of the other. That means that you can write this out as whatever entry this is. Say this is 3, then if A is skew-symmetric, the other entry has to be negative 3. Okay, that's just an example. Okay, so this is an example of a skew-symmetric matrix that's 2 by 2, and for a 3 by 3 matrix, it's the same idea, right? So again, A transpose is flipping in the diagonal, so if that's negative A, all the entries in the diagonal have to be negative of themselves, so that's just going to be 0. The only number that's equal to negative of itself is 0, and otherwise, whatever the entries may happen to be above the diagonal, for example, say it's 1, -1, 2, then the entries below the diagonal have to be the negatives of them. So here you have 2, you flip it, you have to have negative 2. Here you have negative 1, you flip it, you have to have +1. Here you have 1, you flip it, you have to have negative 1. So it's all pretty cool, but one thing is, are these invertible, right? Are we producing invertible skew-symmetric matrices? Because that's what we're interested in our problem. And what's curious is we can actually work this out. So for example, we're going to use the determinant. That's going to be our crucial ingredient. The determinant of this matrix is multiply these two, subtract the product of these two. So that's just going to equal to +9. That's how you find the determinant of a 2 by 2 matrix. It's +9, and so that's non-zero. So our matrix is invertible. Okay, so that's an invertible skew-symmetric matrix, okay? But 2025 is what we want, so that looks a lot more complicated. What about the determinant of this matrix? So I want you to drop a comment right now or think about it. Calculate what the determinant of this is, okay? That's going to be a pretty fun exercise, going to give you some insight into where we're going with this. What is the determinant of this matrix? But let's actually just think in terms of the determinant, because we know that our matrix is invertible. That's an information on the determinant, and we know that it's skew-symmetric. That's A transpose is negative A. So let's try to combine the two. That's going to be our trick, and let's see where we go with that. Okay, so we know that A is invertible. Let's take the determinant on both sides. Okay, we know that's going to be non-zero. So what is the determinant of A transpose? Okay, determinant of A transpose. Well, a crucial property of the determinant is it doesn't change when you take the transpose. Okay, it's one of the properties of determinants. So the determinant of A transpose is equal to the determinant of A. If you actually expand out the formulas, or whatever definition you use, you can use that to show this. So that's the determinant of A. That's actually equal to the determinant of negative A. Now, what's the determinant of negative A? So a misconception, I've seen this happen, sometimes in higher level problems. I've seen it happen, like people will just say, is this equal to negative of the determinant of A? Well, the answer is no. Okay, the answer is no, and you can actually do an example to find that out. For example, if you took this 2 by 2 matrix and took its negative, you would get -3 and +3 here. The determinant would still be +9. It would not be -9. So taking negative of the matrix doesn't necessarily make the determinant negative, okay, of whatever the original determinant was. So we have to actually be careful here. And the way I'm going to show it to you is above. And just want to say, if you're enjoying the content so far, this fun discussion and thinking process, please don't forget to smash that like button and hype the video if it's been recently uploaded. really makes a huge difference. Liking, sharing with other people, and subscribing to the channel. I've got playlists across all topics and levels. And a huge thank you so much to my channel supporters, Alex and Stephan for ongoing Ruby support on Patreon, and Nathan for ongoing Gold support on Patreon, as well as Aman, Rob, Shabeed, and Bernard for their ongoing support as YouTube channel members. You can click the join button for YouTube channel membership. Really makes a world of difference. Small contributions really add up. The exclusive perks, value all support, priority replies to comments, personalized thank you message. If you comment, I can thank you personally. And I'm really grateful also for the support on Patreon, where there's a members only Discord server as well as on YouTube, depending on the level of support. So thank you so much to everyone who supports. It really makes a huge difference, because I do everything on this channel on my own. And let's just get into the video, and let's actually just now understand what happens here. So what is the determinant of negative a? I'm going to do the following trick. Okay, you might have seen this formula already, but maybe this will give you some insight. You're going to get the determinant, and I'm going to show you the symplectic geometry after this. Okay, so don't forget to watch till the end for that. A times negative I, determinant of a times negative I, and by the multiplicative formula of determinants, that's det A times the determinant of negative I. And what is the determinant of negative I? Well, for example, if you have I is a 2 by 2 matrix, you have negative I is just going to be this. The determinant is just going to equal to the product of the diagonal entry is going to be 1. If you take the determinant of a 3 by 3 matrix, negative 1, negative 1, negative 1, you can just see the pattern here. The determinant is a product of the diagonal entries. Every other term when you calculate the determinant is 0, because you're going to choose at least one 0. You pick one entry in each row and each column, multiply them out with a sign. So this is going to be equal to negative 1, because negative 1 times negative 1 times negative 1. And in general, in dimension n, the determinant of in, of negative in, is going to equal to negative 1 power n. Okay, so what that tells you is that this is going to be minus 1 power n times the determinant of a. So that's pretty subtle. That's pretty subtle. And now we're done, because basically the determinant of a is the determinant of negative a, which we know is going to equal to minus 1 power n times the determinant of a. And if a is invertible, the determinant is non-zero, we can cancel from both sides, and we get that 1 is equal to minus 1 power n, and that can only happen when n is even. Okay, so therefore n has to be even. Skew-symmetric invertible matrices can only exist in even dimensions. And I want you to give me an example of, for each n even, give me an example of a skew-symmetric invertible matrix. It'll be so cool if I uploaded this video in 2025, but maybe if you're watching in 2055, 2056, that would be so cool. And then you could sort of think about, like coming up with such an example if your ear is even, coming up with an invertible skew-symmetric matrix. So drop a comment down below, what's an example and n is even. And for symplectic geometry, how does symplectic geometry work? Symplectic geometry is all about symplectic forms, which are essentially a family of such invertible skew-symmetric matrices. For example, what it means is that if you have what are called manifolds, these are higher dimensional shapes. So in 2 dimensions, for example, you can have a sphere, that's the surface of the earth. In 2 dimensions, you could also have a donut. Okay, this is what is called a torus. Okay, sort of a distorted donut with a hole in the middle. So what you do in symplectic geometry is to each point on this surface, you attach, if it's dimension n, you attach an n by n invertible skew-symmetric matrix. This is very rough, and they have to sort of vary in a nice way. They have to continuously vary. And this is what is called a symplectic manifold when you do this. And of course, invertible skew-symmetric n by n matrices only exist in even dimensions by what we explained here. So you could only have symplectic manifolds in even dimensions, not in odd dimensions. So symplectic manifolds are the study of basically only in even dimensions. And that's actually a manifestation of this problem, that you can't have symplectic manifolds in odd dimensions. Now I've got 2 fun videos for you. You're going to love these videos. The first one is if you have a pair of 2 by 2 matrices A and B, then AB minus BA may not be 0, right? AB may not be BA. 2 matrices do not commute in general. AB is not necessarily BA, but the square is always a constant times the 2 by 2 identity matrix. And this is very special to 2 by 2 matrices, not true for 3 by 3 and higher. Want to see the proof of that? It's so fun. It's such an ingenious trick. Check it out. It's going to pop up on the screen here. And another fun video, if you're interested and fascinated by this topology, you want to dive into it, you maybe don't understand it well, here's the introduction to compactness. In topology, what is compactness? What are open sets? How does topology work? It's going to pop up on the screen here. Have an amazing day. I'll check you out in either of those 2 videos. And math everywhere. I'm super excited to see you soon.